Hi, welcome back. We are going to, for this little mini lesson, talk about our non-specific defenses. The book also uses the term innate defenses, which means kind of inborn. You have these from when you are born. You don't have to be exposed to any particular pathogen to get protection. So this table kind of shows a list of the innate or non-specific defenses we're going to talk about. The first one is our skin. Our physical barriers. So this is going to be your mucous membranes, your thin skin, your thick skin, your hair, your exocrine glands, your like sebaceous glands and sweat glands. All of these serve to be a first line of defense for any invading pathogen, no matter its identity. So if you remember skin, the outermost layer is dead, keratinized, many layers of that stratum corneum. It makes it really hard for things to penetrate into that underlying blood, vascular tissue. So that's why keeping an intact physical barrier is so important to reducing your chances of infection, because once you break that, it could be a cut or a scrape or a zit or a blister or anything that could open up a burn, that could open up that physical barrier, invites more opportunities for pathogens to get into your system. All right, so that's our physical barrier. The next non-specific defense we'll talk about quickly are phagocytes, and we've seen phagocytes before. You should be fairly familiar with cells that have the ability to do phagocytosis. So some of our white blood cells, our leukocytes, were phagocytic. So if you remember, neutrophils, eosinophils, and monocytes are all white blood cells that have phagocytic capabilities. And then we have our fixed and free macrophages. And so these are cells that can go around and they can remove dead cells, cell debris. They can munch up dead red blood cells and recycle those components, but they also have the ability to engulf bacteria. And so we'll see how some of these phagocytes can actually serve a purpose for our specific or adaptive immune responses. So we'll see those a little bit later. I'm going to do another I have more specific slides on interferons, complement, and inflammatory response. So before I go away from this slide, I want to talk a little bit about fever. So fever in this table is the last non-specific defense in here. So let me flip to that section. So fever is any time that your body maintains a higher than normal body temperature, usually 99 plus would be considered a fever. And if you remember from I think 231 we talked about it, and 232 we were talking about the hypothalamus. We have that suprachiasmatic nucleus somewhere in the hypothalamus was your thermostat. So we have information coming in, our hypothalamus processes that and sets our body temperature 37 degrees Celsius, 98.6 degrees Fahrenheit on average. Some people can run a little bit colder, a little bit warmer, but that would be your normal body temperature. Our cells, our enzymes, everything works good at that temperature. Unfortunately, pathogens do as well. So viral replication happens really good at 37 degrees. Bacterial replication happens really good at 37 degrees. So our body temperature is good for pathogens' replication temperature. So fever is when our bodies can increase that temperature, and we have a little bit broader optimal range for our enzymes and cells functioning, but viruses and bacteria do not. So if we can withstand body temperatures of 101, 102, 103, it may be uncomfortable for us. Our cells actually work pretty well at those temperatures. As remember, temperature increases, enzymatic activity increases, metabolism increases, white blood cells might be a little bit more active. So that's good for us, and it's bad for these pathogens. Bacteria don't replicate that well at higher temperatures. Viruses really don't replicate that well at higher temperatures. They're more sensitive to those changes, and so it allows our body to kind of take a second chance at trying to overcome that pathogen. So fevers are actually beneficial for us. They can be dangerous if they get too high, right? So if your fever goes 106, 107, 108, now you're starting to interfere with your own cells' functionality. And we don't want to be denaturing our enzymes and breaking down our metabolic processes. So within limits, fevers can actually be beneficial. So don't always reach for that fever reducer right away at the first signs of a fever. Just kind of let your body do what it's supposed to do. It's made to fight off these invaders. But be careful because you don't want it to get too high for too long, because then that could be dangerous to your own cells. So that's why fever is a non-specific defense, because it can be produced by multiple types of pathogens, whether it's multiple types of viruses, multiple types of bacteria, fungal infections, amoeba infections, parasitic infections. Fever is a common response to some kind of infection. The things that trigger that resetting of the hypothalamus, the chemicals, and there's lots of different kinds, but collectively they're called pyogens. Think of like a pyromaniac, somebody who loves fire. Pyro means heat formation, so a pyrogen is a heat generating chemical. They could be just the presence of the virus. They could be a virally infected cell releases these chemicals that act as pyrogens that crank up the thermostat, and then your body's like, oh, 100 degrees now, I'm at 98.6, 98.6 is too cold, so you got to shiver, right? So you get the chills. You feel cold at 98.6, and so your body is contracting your skeletal muscles, raising your overall body temperature to try to reach that new set normal, say at 100, 101 degree Fahrenheit. And so then you get the fever, you're feeling hot to the touch, your thermometer is going to tell you that you are hot. And then once the fever breaks or the pyrogens go away, then you're like, ugh, it's 101 degrees, and your hypothalamus set back to 98.6. Then you start sweating to cool yourself off, because you got to do that thermoregulation, get back to 98.6 degrees. And then sometimes fevers cycle that way. Sometimes there's one fever and it goes away. So each pathogen might be a little bit different in how it gets your body into producing those fevers. Okay, so we're going to move on into a little bit more detail on some of these other non-specific defenses. So this first one is called immunological surveillance. We saw this a little bit earlier when we were talking about the different types of lymphocytes. So natural killer cells are responsible for this immunological surveillance. So here in the micrograph, this N cell here, this is a natural killer cell. And the T here, T stands for target. So this is what it's trying to attack. So let's say you have an abnormal cell, all right, so that's in step one. It is showing on its little plasma membrane surface those red antigens. So remember, antigens are proteins, they're on the surface. Antibody generating is where that word comes from, but they are like little name tags. And so if those little name tag on an infected cell says, I'm not normal, I'm an abnormal antigen, that is what the natural killer cells recognize. So they are going around, just normal natural killer cells, and their job is to just kind of read the surface antigens on your cells. And if you're normal, they'll ignore you. If your antigens are abnormal, they will attack you. And that abnormal antigen could be from a viral infection, or sometimes it could be from a cancerous cell. So if your cell is turned cancerous, it's gone rogue, it's putting up all of these weird antigens, that's a signal for your natural killer cells to destroy it. So whatever way the cell is abnormal, it's going to be presenting these abnormal antigens on the surface, those little red circles. The natural killer cell will recognize that. It comes into very close contact, like we can see over here, very close contact between the two plasma membranes. Golgi, right? So if you remember that organelle, the Golgi is kind of all these flat sacks of membranes, and they got all the little vesicles. It will actually rotate like a turret on a tank. It will rotate and face that connection, and it will start sending a whole bunch of these little vesicles, like we can see here, all of these guys, all those little vesicles towards the surface to exocytose a chemical called perforin. So perforin, don't want to block out the name, perforin is a molecule that when it comes into contact with a plasma membrane of the target cell, it makes little holes. It perforates it. It pops holes in that target abnormal cell. And if your plasma membrane has holes in it, you cannot maintain structural integrity, you are going to lyse. And so that's what we get as a result, is a killed abnormal cell. Okay, pretty cool. So that's your immunological surveillance done by natural killer cells, a type of lymphocyte that goes and roams around looking for normal cells, ignores those, finds the abnormal cells, kills those. And why this is under non-specific defenses is because it will do that for any type of abnormal cell. It doesn't have to be a particular virus that it will attack and ignore other virally infected cells. Any abnormal cell will be attacked by your natural killer cells. All right, immunological surveillance. Okay, so our next non-specific defense is what we call interferon. So interferon is a pretty cool chemical weapon that we have in viral infected cells. So if your cell is infected by a virus. So there are a couple different types. We'll go through the different types of interferon. Okay, I got my notes here. So we have alpha, beta, and gamma. So here's alpha, right? So alpha interferon is the main one that I'm going to be talking about when we're talking about the role against viruses. And then we have beta interferon. Beta interferon helps to slow inflammation in damaged areas. It's secreted by fibroblasts. So if you remember, those are the cells that help generate our collagen, elastic, and reticular fibers. And then we have gamma interferon, which is secreted by T cells and natural killer cells, and it helps to stimulate macrophage activity. So you might have a virally infected cell, natural killer cells kill it, they secrete this interferon gamma, it comes in and it activates these macrophages. So like, hey, come and clean up this mess that I'm making because I'm destroying all of these virally infected cells. Okay, so there's different roles for these different interferons. I'm going to talk more specifically about the alpha interferon because it's really cool the way that it works against viruses. So that's why I put this picture, the second picture here on the screen. It's not one that's in your textbook, I believe. So let's say you have a cell, right? We'll call it cell A. And cell A has been infected by a virus. And it's like, there's nothing I can do. The virus got in me. It's replicating. It's making more of itself. I'm kind of a goner. But what I can do before the virus releases and goes and infects all of the neighbors is I will release my alpha interferon, these little red dots here. So these little red dots will go to their neighbors, right? So it's like warning, hey, you guys, a virus is coming, protect yourself. So these neighboring cells have receptors, those are little green guys, these little receptors will pick up this alpha interferon. When that happens, it triggers metabolic processes, signal transduction within the cell to make antiviral protective molecules. So if a virus does get in, like in this middle one, it will kill the virus or cut up its nucleic acid. So that's this one, destroys the RNA to reduce the protein. It could, if a neighboring cell happens to be infected, it could trigger apoptosis, which is going to cause the cell to destroy itself before it has a chance to make more viral proteins. And it can trigger these macrophages. My face is kind of covering up. It'll activate the macrophages to then go and try to find more virally infected cells and to destroy those. So interferon is kind of like an altruistic way that your cells can protect their neighbors so they don't get the virus infected. They're like, I'm already a goner. I'm going to try to protect you guys. So that's the way interferon works. All right. And then our last, not our last one, second to the last non-specific defense, we're going to do complement and then inflammation. So complement is a set of kind of a cascade event that happens when you're infected with some bacteria. So this is more of a target against bacterial infections, whereas interferon was good for viral infections. So complement is called complement because it complements your specific defenses. So it works best when antibodies have already been produced by a specific immune response. So I'm going to go through the classical pathway first. There's an alternate pathway, and then the textbook also has what's called the lectin pathway, which is not pictured here, but you have it in your text. So the classical pathway, let's say you have a bacterium and it has been covered by antibodies, right? So we can see that little bacteria there. Antibodies on their little stalk piece, they will have, like right here, they will have a little attachment point. It's called the complement binding site. So you have these complement proteins, this big C1 protein is circulating through your bloodstream. It's just part of your plasma proteins. When it comes into contact with that complement binding site, the C1 binds to those little stalks of your antibody and it becomes an enzyme. And so that it will enzymatically drive this cascade of these other complementary proteins, the C2, 3, 4, C3b, and then what they are 2, 3, and 4, and then they convert into what's called C3b. Okay. C3b then kind of hunkers down and attaches itself to the surface of the bacterial cell wall. So then the C3b then in this transduction pathway becomes enzymatic, and complement proteins 5 through 9 will then be enzymatically converted into what's called the membrane attack complex, MAC. So the membrane attack complex pops holes in the bacterial cell wall and destroys the cell, just like the perforin molecule from the natural killer cells popped holes in those virally infected cells or cancer cells. The MAC, the membrane attack complex, pops holes in the bacterial cells, and then the cell lyses, and a dead bacterial cell is a good bacterial cell as far as a pathogen is concerned. So that's what we call the classical pathway. It happens very quickly. When you have bound antibodies from the B cells, you do this process very quickly and you pop the cell. There are alternative pathways in the lectin pathway where we have different triggers. So in this case, properdin, factor B and factor D just are other things that can be circulating around. They will end up activating the C3b, which will then be able to produce the membrane attack complex. And with the lectin pathway, it's just a little bit different. So you have, however it gets started, your goal is to produce that membrane attack complex, which will pop holes in the cell and kill the bacteria. And it's complementing processes that are already taking place, either by bound antibodies or circulating other immune factors. All right, and our last non-specific defense is inflammation, and you'll have to reference your book since my head looks like it's cutting off that last piece of the process there, but that's okay. You have it in your book. So inflammation is a good thing. Over-triggered inflammation, like in this hives rash, and it looks like this was an infected tattoo, yikes. But you can see the redness and swelling around, that would be the inflammation part. But inflammation is a good thing. It's part of your first line of defense when you get tissue damage or infection or toxins being released by a pathogen. It is a way for your tissues to try to heal itself. So we start with a problem. The problem is your tissues are damaged. That's going to break open cells. It's going to introduce bacteria. It is going to trigger your mast cells, right? So if you remember mast cells from 231, they were some of these cells. They have these grains of histamine and heparin. They release those mast cells to produce those 4 cardinal signs of inflammation, right? So redness, swelling, heat, and pain. We saw that back in 231. So with these things, the redness is due to the vasodilation, increased blood flow. That is also the cause of the heat, because you have more warm blood going to the area. Swelling, because the vessels are a little bit more permeable, right? So increased permeability. We have fluid leaking into the tissues. That's the swelling. And then we get pain directly from these mast cell chemicals are triggering your pain receptors. The swelling will be pushing on sensory neurons. And so those are the 4 signs of inflammation. It will, if the damage to blood vessel, which is likely, you'll get clot formation and repair. That was part of our hemostasis. And these chemicals will also attract your phagocytes, so neutrophils, monocytes, other macrophages. They will release their cytokines to attract more neutrophils and monocytes and macrophages. And then we'll get tissue repair and the removal of the pathogen, which you can't see because my face is there. And so that will eventually lead to a corrective response, and your tissue will be repaired and the inflammation will go away. Unfortunately, a lot of times people associate inflammation with a bad situation because it is an incorrect response to something, like an allergic response or hives. You know, if you are allergic to poison oak, like I am really bad, I get these huge rashes and it's really itchy and it's overproduction of this inflammatory response, or some autoimmune diseases like rheumatoid arthritis or digestive issues, irritable bowel, those types of things. They are overactive inflammatory responses. And so it's a good thing when it does what it's supposed to do. It can be a bad thing when it's happening when it's not supposed to do that, when there's actually no trauma or there's no infection. If you get inflammation in tissues where there's not a problem, then it's going to make itself a problem. So remember, inflammation is good when it's working as it's supposed to. Inflammation can be bad if it is in a non-threatening situation where there is no tissue damage or trauma. All right. I think that is it for this little mini lesson on our non-specific defenses. Again, just to wrap up what's going on, the reason why these are all collectively put into this category of non-specific defenses is because they will function no matter the identity of the antigen. So whether it is a virus, coronavirus, flu virus, chickenpox virus, whether it's a bacteria, E. coli or salmonella or tuberculosis, whether it is a worm or an amoeba or a fungal spore or whatever, all of these non-specific defenses will do their thing no matter the identity of the pathogen or the thing that's causing the problem. That's the idea of these innate or non-specific defenses. Okay, so the next couple lessons will be on the specifics of the specific defenses or the adaptive immune response. We'll see that next.